Hello everyone, this is Engineer Amani Saeed. I will share with you today our research in Marlog Conference, Marlog14 2025. The research on an essential topic in marine engineering, the investigation of the soil structure interaction on quay walls, and how we use finite element modeling in this regard. I will walk you through our parametric study, using finite element modeling to grasp how these quay walls respond or behave under the different types of soil and also under extra loads, and what we need to do to satisfy the future demands. As an introduction, let's talk about the structural strengthening. It's an effective and visible approach, especially for marine structures. It can enhance the structural capacity of these marine structures to meet the increasing demands of the marine industry, while also facilitating the repair of the damaged structures after an incident like ship hit or natural diseases like seismic events. In this context, developing methodologies that can simulate the real-life condition to improve the reliability of assessment when investigating the soil structure interaction, load increment, and the suitable strengthening system is very important. One of the optimal approach in this regard is the numerical modeling using finite element softwares such as Plaxis, Midas, Abacus, and ANSYS. Now, let's discuss the problem at hand. Maritime transportation is the lifeblood of global trade. As the cargo grows, the size of the ships also increases, necessitating the upgrading of port infrastructures. This requires deeper quay walls, bigger cranes, and more storage space. All of this increases the loads on the quay wall, and here is the challenge. Quay walls interact with the soil in a complicated manner. If we don't account for it adequately, we risk structural problems, expensive repairs, and operating downtime. And here is where our research comes in. To meet future demands, we set out to investigate how these quay walls behave under extra loads in line with various types of soil and material models. So, we implemented finite element models. Finite element modeling is a sophisticated computational tool that allows us to simulate the real-world condition in a virtual environment. This will lead us to our objective. Our research objective to tackle this problem by assessing the soil structure interaction for an existing quay wall, which need to be upgraded to accommodate the additional loads caused by the increasing in the depth of the quay wall and also by the crane loads increment. Finite element models were developed to verify the case study and analyze the impact of various material models along with different soil profiles on the mentioned case. In addition to performing a parametric analysis on the increment of the crane loads and from the deepening of the quay wall to achieve this goal. Finite element models conserve time, resource, and effort. Think about it as a digital lab where you can test these quay walls, how they respond under the different loads and the different soil conditions, without the need for the costly physical expert. To explain more precisely, the research methodology is built on three key components. The first is a verification approach, in which we use two case studies to verify. A quay wall in Rotterdam, which provide field measurement and numerical model results, and a quay wall in East Port Port, which provide results from two research based on two different soil profiles and two different material models. The second approach is a comparative analysis for the East Port quay wall, which include comparing between different material models within the same soil profile, as well as comparing the different soil profiles within the same material model. and this to figure out the optimal material model that we can use in the third stage, which is the parametric study. Parametric study for the crane loads and the wall depth increment in case of drained and undrained conditions. And this to figure out the increment impact, so we can select the appropriate system for strengthening or upgrading. We employed Plaxis 3D to create detailed models, but before we could trust our models, we needed to verify them against the real-world data. For the deep sea quay wall at Rotterdam, which is cited in Muhammad Kamal 2021, the system of the quay wall consists of king piles as a front wall and sheet piles for the back anchorage system, in addition to a number of rows of spaced piles. The soil profile and construction phases were as shown. Here are our results from Plaxis 3D. The total soil displacement is reported in the published research as 132 mm, while our model displayed 128 mm, which is resulting in a discrepancy of around -3%. In the terms of the horizontal displacement, the published value was 59 mm, while our model played by 53 mm, which indicating a discrepancy of nearly -9.5%. The following table show a comparison for the top horizontal displacement between the field measurement versus the numerical models results from Muhammad Kamal and from our models. For example, in the overloading phases, the computed displacement is 72.66 mm, whereas the published value is 72.07 mm, resulting in a discrepancy of around 0.8%. While regarding the field measurement, the displacement was 77.84 mm, and which indicating a difference of nearly -6.6%. The following chart displayed that our results laying between the maximum and the minimum measured value from the field measurement and are also closely aligned with the published research results. For the East Boursaid Port Diaphragm Quay Wall Container Terminal, the quay wall system consists of a concrete T-shaped diaphragm parrot wall for the front and the back wall, in addition to 2 rows of parrots. The soil profile shown cited in El Gendi et al. 2016 and was defined as more column material model, and we have designated it with soil profile A. The other soil profile shown cited in Umayma Hamid et al. 2017 and was defined as hardening soil material model, and we have designated it with soil profile B. The construction sequences divided mainly into construction, excavation, dredging, and applying loads. Here are our results for the soil profile A. Regarding the horizontal displacement, our models displayed 23 cm, while the reported one was 18 cm, and this resulting in a discrepancy of nearly 27%. While for the normal force, our models displayed 15.2 ton, while the reported one was 14.6 ton, and this resulting in a discrepancy of around 4.1%. Finally, for the bending moment, our models resulting in 15.6 ton meter, while the reported one was 17 ton meter, and this resulting in a variance of around 8%. Here are our results for soil profile B. The following tables show a comparison between Umayma Hamid result and our model's result for the phases in case of drained and undrained condition. For the undrained condition, the majority of the phases results in a discrepancies below 5%, which is an accepted margin of error. While for the drained condition, the majority of the phases indicating discrepancies below 10%, which is also an accepted margin of error. Now, let's move on to the comparative study. Proceeding with the East Port-Said diaphragm quay wall container terminal. In this step, we turned soil profile A from more column material model to hardening soil material model, as well as for the soil profile B, we turned it from hardening soil material model to more column material model. Then we created our 3D Plexus models to compare between the different material models within the same soil profile for soil profile A and B, as well as comparing between the different soil profiles within the same material model for material model, more column, and hardening soil. What did we find? Here are our results. More column displayed a significant increase in horizontal displacement, approximately 280%. In contrast, the increase in normal force was around 11%, while the bending moment increased by about 80% when compared to hardening soil material model. And here are our results for the soil profiles. Soil profile A displayed minimal relatively horizontal displacement, approximately -65%, while for the normal force, it demonstrated a decreased value of around -15%, and for the bending moment, it showed a reduced value also of about 30%. From all of this, it's evident that the changes for the hardening soil material model are less pronounced than those for more column, and for that we will proceeding with the hardening soil material model with the next stage. Next, we will cover the parametric study. Proceeding with the East Port-Said diaphragm quay wall container terminal. What happens if we increase the loads on the quay walls? To answer this question, we developed two vital trials on the increment of the crane loads and the dredging level for the drained and undrained conditions with using of hardening soil material models. The following tables show us the increment methodology. For the crane loads, we increased the loads from 80 ton per meter to 160 ton per meter, which is doubling of the load. Also for the horizontal load, we increase it from 8 ton per meter to 16 ton per meter. Regarding the dredging level increment, we increased the level from -18 to -24, which is 6 meters beyond the original depth. What did we find? Here are our results. For the crane loads increment, when the crane load increased from 80 ton per meter to 160 ton per meter, which is doubling of the load, this leads to an increase in the horizontal displacement by about 26%, and for the normal force by 30%, while for the bending moment was 22%. Regarding the dredging level increment, when we increased the depth or the level of dredging from -18 to -24, which is 6 meter increment of the original depth, the horizontal displacement increases by 70%, and the normal force increases by 20%, while for the bending moment the increases was 55%. So, What can we acquire from all of this? Regarding the deep sea quay wall at Rotterdam, most of the results are within the accepted difference with the calculated results and the field results published by Mohammed Kamal, with average difference within 10%, which is an accepted margin of error, and this difference was due to the different versions of softwares and related to the available data from the authors. Regarding the Bursaid Port East diaphragm quay wall, most of the results are within the accepted difference with the calculated results published by Umay Mohammed. Most of the results indicated discrepancies less than 10%, which is an accepted margin of error. And this difference is also due to the different versions of softwares and related to the available data from the author. In addition to indicating that hardening soil material model considered the most effective material model when we dealing with the clay soil. For the comparative study, the results indicate that more column material model displayed higher results than hardening soil material model, especially for the horizontal displacement, showing that the more column material model is more conservative due to its relative insufficiency in soil definition parameters compared to hardening soil material model, and that's why we're proceeding with the hardening soil material model. Finally, for the parametric study, the result is displayed that the deepening in front of the quay wall has a larger impact than the increment of the crane loads. For instance, the bending moment escalates by 22% when the crane loads are doubled. However, it grows by 55% when the deepening reaches 6 meters beyond the initial depth. So, this research gives engineers the tools they need to design stronger, more resilient quay walls, and selecting the appropriate upgrading or repairing system based on the impact of the different factors. To make these quay walls can handle or accommodate the future needs. But our work doesn't stop here. Looking ahead, we want to explore new ways to strengthen the quay walls to accommodate these extra loads or repair after an incident. In addition to comparing these new methods with the traditional ones, to demonstrate the advantage for each of them in a visibility study. Moreover, we highly recommend to employing machine learning techniques to predict the optimum design required for upgrading or repairing these quay walls by these new methods, as nowadays the AI and machine learning techniques have a large impact in our life. Thank you for your attention. I would like to answer any question you have.